Hello everyone, my name is Su Jiping. I'm from Group 8, and our group member have Xiangyao Song and Sang Yizhen. This is our final project for the computer vision class, and our project name is Key Point Guided Attention for Adaptive Feature Pyramid Networks. Okay, so the Feature Pyramid Network, or FPN, is a widely used deep learning architecture designed to address the challenges of multi-scale targets in computer vision tasks like object detection or semantic segmentation. And recent models like the YOLO series or MaskRCNN both leverage this technique to achieve a better performance in multi-scale object detection or segmentation. On the right side, we can see the classical FPN framework, which is basically a top-down pathway. It merges the low-level but high-resolution features with the high-level but more contextual semantic features together to enable the model have a better performance in multi-scale object. However, previous work have shown that such multi-level structure may contain noisy features or information redundancy. Therefore, recent works have proposed multiple methods to further improve the FPN framework. First, the PA-NET, or Path Aggregation Network, adds a bottom-up path to augment the standard FPN and improve the feature propagation from lower layers. Next, the NAS FPN automatically designed the FPN structure using the neural architecture search, and it's optimized for a specific task. Finally, the BiFPN, or bidirectional feature pyramid network, efficiently fuse multi-scale feature with a bidirectional approach and introduce a weighted feature fusion where the importance of each route is learned during the training. And this allows the FPN itself to focus on the essential connection inside the pyramid. However, we can see that these methods all focus on the pyramid level of the structure, and wonder if we can improve the FPN structure from a image level. Okay, so to improve the FPN in the image level, we come up with the idea to leverage the surf key points to identify the salient image regions to guide the FPN framework. And SURF, the speeded up robust features, is actually quite like SIFT. It can detect key points in an image by finding areas of high variation, like edges or corners, that are invariant to transformation, such as rotation or scaling. But compared to SIFT, SURF is generally faster due to its reliance on box filters for approximating Gaussian derivatives, but it may be less effective in certain circumstances. So bottom here we have a sample image from the Cityscapes dataset on the left side, and its corresponding image with the surf key points on the right side. We can see that the important features like the cars or vehicles or the buildings have a lot of key points, and the less relevant area like the bottom here have nearly no key points. So we believe this can help us to guide FPN to focus on the most important area. Okay, so in order to leverage these key points to guide the FPN layers, we computed the density of the key points in each image region to obtain an heat map MK. And this MK is calculated by the equation 1, which is basically counting how many key points lies in the grid of the heat map, and then normalize it with the highest value. And this map has the same shape of the FPN P2 layer, which is the highest resolution layer. And this is because that this layer contains the most detailed visual feature and should receive the finest attention. And in practice, we also apply a Gaussian filter to smooth out the map, let the attention area be more broad. And this density map will indicate the relative importance or saliency of each image region. So here are the generated sample of the key points density map. On the left side is another Cityscapes dataset image, and on the right side is the corresponding computed key point density map. Again, we can see that the salient regions such as the cars or the buildings receive higher attention in yellow or red in the heat map, while less significant areas like the roads are black, which are assigned lower focus. Okay, so for each layer following P2, we want to apply another additional gradient map to enhance the attention area, because these layers often contain more global information and require less targeted attention. And the gradient map is calculated as equation 2. So for each layer, we have the attention map calculate with equation 3, which is basically for higher layers, we have more gradient map on it. And finally, the map is applied to each layer of the FPN using the element-wise multiplication. And here we can see the sample image shown before and with the gradient map applied. So from left to right, we have the P2, P3, P4, and P5 layer. And P6 is omitted here because all of its values are 1. Next, for the experiments, we use the instance segmentation benchmark datasets, cityscapes. And this dataset contains numerous images of different cities which are high resolution, and the task is to do instance segmentation to identify the vehicles or the pedestrian on the road. And for the model, we use the mask RCNN model, which contains a classic FPN insights let us to modify. Okay, so here are the results. We followed the standard practice to use 3 different metrics: the COCO detection, COCO segmentation, and the cityscapes also for segmentation metrics. First, in the detection parts, we were able to improve the baseline model with a 0.3% improvements, and we have a 1.3 performance improvements in the MAP75. But in the MAP50 and the MAP small and MAP median, our model led to some decreasement. Next, in the segmentation area, our model performed quite well. We have overall improvements and a 0.5% in the MAP. And specifically in the MAP small, we have a 1.2% improvements. This means that our model were able to improve the mask RCNN segmentation ability, especially in the small objects. Finally, in the cityscapes datasets, we also have some improvements. In the MAP, we have a 0.52% improvements, and APF50, we have a 0.82 improvements. Next, we have the ablation study. So previously, we have mentioned that we have used a Gaussian filter to smooth out the generated heat map. And here we done a ablation study on the sigma value for the Gaussian filter. And a higher sigma value will produce a smoother and more generalized heat map, while a lower sigma value will result in a more precise and more targeted heat map. And in the previous result we see, we use a sigma of 9. And here we have different sigma value compared to the baseline. And we can see that the sigma value have actually quite some impact to the performance. Here we only list out the most important metrics, and we have the mean improvement here. We can see that with sigma equals to 9 or 11, we can bring quite some improvement overall. But when using a smaller sigma or a higher sigma, the performance will start to decrease. Okay, so here we conduct another ablation study on the attention strategy. So previously, our method used a targeted or more fine-grained attention map on the higher resolution FPN layer, like P2 or P3. And here we do an inverted strategy where higher resolution FPN layer will receive broader attention, and the equation will look like this. Okay, on the right side, we can see that this method basically brought down the performance over the baseline, and which is quite intuitive because this method will basically let the noisy or redundant information in the high resolution layer flow through and block down the more important and global or spatial information in the high level or low resolution FPN layer like P5 or P6. Okay, so in conclusion, in this project, we introduced an attention method based on the served key points to guide FPN to focus on salient features. And the attention map provide the most targeted attention for higher resolution P2 layer and gradually enlarge the focus area for later layers to preserve more global information. And our result demonstrated the effectiveness of this method on the cityscapes dataset, achieving notable improvement in both detection and segmentation performance for the mask Gaussian model. Thank you.